We're going to get into talking about complex and imaginary numbers. First, we're going to look at some quadratics. So first of all, if we wanted to solve the quadratic equation x squared minus 2x minus 3, this is one that's easily factorable. We can factor that x squared into x and x, and then 3 factors into 3 and 1. If we go negative 3 plus 1, that'll make the negative 2x that's in the middle. By the zero product property, of course, we can set each factor equal to 0 and solve them. So we'll get x is equal to 3 or x is equal to negative 1. Sometimes, just by changing one number in the equation, all of a sudden we can't factor it anymore. But that's okay because we can solve by completing the square or by using the quadratic formula. This one I'm going to solve by completing the square. Just to review that. First off, we move the 2 over to the other side to make room for completing the square. In order to complete the square, we want to rewrite this entire trinomial as a perfect square, so we'll need half of that middle number, which is 1, and then when we square it, we'll add 1 to the left side. Whatever we add to the left, we should add to the right as well. And we got that 3 there. Next step is just solving the equation, so we square root both sides, and we'll get x minus 1 is equal to plus or minus the square root of 3. Add 1 to both sides, and we're finished. 1 plus or minus the square root of 3 are our two solutions. So let's try one more, this time with the quadratic formula. So that would be x equals negative b, which is negative 2, plus or minus the square root of b squared, that negative 2 squared, minus 4ac, so in this case a is 1 and c is 2, all over 2a, so 2 times 1. And we start to simplify. We'll get 2 plus or minus the square root of negative 2 squared is 4, and 4 times 1 times 2 is 8, all over 2 times 1, which is 2. So we'll get 2 plus or minus the square root of negative 4 over 2. And this is where we begin to run into problems, right here with this square root of negative 4. Now, we're not the first ones to run into this problem. Descartes and others, when they first started exploring polynomials, realized that this caused a problem because we have a second degree polynomial. It's supposed to have 2 solutions to it, but we can't take the square root of negative 4. It's not a real, actual, good, honest to goodness number. So they imagined a new number for us. And this is where imaginary numbers come in. First of all, we have the imaginary unit, which we label as I, this lowercase I, and that is the square root of negative 1. So any imaginary number, if we have any positive number a, and we're taking the square root of negative a, then the imaginary number would be just like taking the square root of a and tacking the I on to the end of that. A complex number is any number written in the form a plus bi, where a is a real number and b is a real number. So what makes it complex is that this entire number has a real part and an imaginary part to it. So going back to our problem where we had x equals 2 plus or minus the square root of negative 4i, with imaginary numbers we have a way to express this. This square root of negative 4, we can rewrite that using imaginary numbers as the square root of 4i. Then continue simplifying. So we'll have 2 plus or minus square root of 4 is just 2i over 2. Factor a 2 out of the numerator, so we'll have 1 plus or minus 1i over 2. These guys will cancel, and then we can simplify it to 1 plus or minus I. 2 complex solutions. Now, complex numbers, they are numbers, they're just not real, but they're numbers, so we can do number things to them, like add, subtract, multiply, and divide. When we want to add or subtract, all we have to do is combine like terms. If we are adding the complex number 2 minus 3i to 6 plus 7i, we can look at it as 2 minus 3i plus 6 plus 7i, and collect like terms. So the 2 and the 6. And then we'll also have the negative 3i and the positive 7i. Combining the like terms, we get 8. And over here, that would make plus 4 of the i's. Be careful when you have subtraction in there. The most common mistake I see is people will go, oh, 2 minus 6 makes negative 4. And then I got negative 3i plus 7i makes plus 4i. And you completely ignore the minus that's in the middle there. Instead, what you want to do is just distribute the negative sign first. Just slow down. It's worth taking the extra couple seconds to distribute that negative to minus 6, minus 7i. Then your eyes won't mess with you, and you're much better at combining the like terms of 2 minus 6 is negative 4. And then negative 3i minus that 7i makes minus 10i. When it comes to multiplying, we treat it like any other multiplication of binomials, like foiling. So 2 times the 6 will give us 12. 2 times the 7i is 14i. And then with the negative 3, we get negative 18i and negative 21i squared. Now when we go to combine like terms, it looks like the only like terms we have are right here. So we'll add together 14i minus 18i leaves us with negative 4i. But we do have this negative 21i squared. And I want to take a closer look at what I squared is. First of all, remember that we defined I to be the square root of negative 1. So if I want to find out what I squared is, I'm going to take the square root of negative 1 and square that. Those two will cancel, so I squared is going to equal negative 1. Back to our problem, that means this I squared is really just negative 1. So we'll have minus 21 times negative 1, which ends up turning it into a plus, of course. Now finish combining like terms with that 21 and the 12, and we'll get 33 minus 4i. When we have that perfect square, treat it like binomials again. If you feel more comfortable doing 2 minus 3i times 2 minus 3i and foiling things out that way, go ahead. Or if you just remember the pattern, we'll square the first thing. Take double the product of these two, so negative 6i, but there will be 2 of them, so negative 12i. And then squaring the last thing, and make a positive 9i squared. When we go to combine the like terms, remember that this I squared is really going to turn into a negative 1, making this minus 9 instead of plus 9. So 4 minus 9 gives us negative 5, and we'll still have the minus 12i after that. And of course, the pattern that we like the most is when everything's the same except for that plus or minus in the middle, because then we'll end up with the difference of 2 squares. So we'll have 4 minus the 9i squared. And again, we have that I squared, which is going to turn into negative 1, making that minus now a plus 9. And this answer will be 13. Now this is actually kind of an interesting result, because any other time that we were doing arithmetic with complex numbers, when we were adding and subtracting and multiplying, those all resulted in other complex numbers. But now, when we're multiplying two complex numbers together, we end up with a solution or an answer that is now real. And that's fairly interesting. And it'll only happen when we're multiplying together two complex factors that look like this, where all the numbers are the same, but one of them has plus in the middle and the other one has minus in the middle. For that case, these two factors have a special name. They're called complex conjugates. And complex conjugates are going to have the form of a plus bi and a minus bi. All right, so that only thing that's different is a plus and a minus in the middle. And when you multiply them together, it ends up being not complex anymore, but now real.